We are producing more and more data, and because of AI, the volume of data is growing exponentially. So here's a quick estimate. According to the International Energy Agency, by 2030, the power demanded of data centers is expected to rise 945 billion kilowatt hours, which for scale is about twice of the German annually electricity use. And for me, one of the most interesting facts, when it comes to data, about 90% of the energy is used for transport the data between storage and the processor, meaning the constant movement of bits back and forth burns most of the power. However, there's something that we can do about that. So-called neuromorphic chips. They process data right where it's stored, meaning less energy is used and processing is up to 400 times faster according to the company I'm visiting today. I'm going near Dresden in Germany, where a company sits that develops and manufactures these chips. And we're about to see how the whole thing works, where it's already being used, and of course what the future potential looks like. And with that, welcome to the German Science Guy. I'm Dr. Jakob Botton, and in Germany we say Los geht's! The company TECHiFAB developed neuromorphic chips, and these neuromorphic chips can process an incredible amount of data extremely quick, in real time, and in a resource-efficient manner. But how do they work? Conventional computer chips consist of many transistors, small electrical switches made of the semiconductor material silicon. With semiconductor materials, it is possible to control electrical conductivity. An electrical signal applied to the transistor determines whether current can flow or not. This represents the binary state 1, current flows, and 0, current does not flow. Billions of these transistors are interconnected on a single chip to form logical gates. So logical gates are a combination of these switches that, when connected together, can perform calculation. An example of a very simple logic gate would be an AND gate. You have multiple input signals, and only if all of these input signals are 1 does the gate output a 1. And I know it's really crazy and not that easy to imagine, but by combining these simple gates, you can actually build the incredible complex programs we know today on our computers and smartphones. So this process describes the processing of information, in other words, computation. But now the information also has to be transferred to a storage medium and saved. That takes energy, which is why TECHiFAB has a completely new approach.
Neuromorphic chips contain a processing unit that processes and stores data in the same location. That is what makes neuromorphic chips special.
To achieve this processing and storage of data in a single location, the TECHiFAB team took a closer look at certain processes in the human brain. The chips in fact work similarly to the human brain, in particular neuroplasticity, that is the flexibility of nerve cells. In other words, new connections between synapses can be formed or broken down. These connections can also strengthen or weaken, which directly influences the conductivity of the signals. And this property is also shared by the so-called memristors, located on the neuromorphic chips. The name memristor is a combination of memory and resistor. These memristors serve a similar purpose to transistors on neuromorphic chips, but they actually function somewhat differently.
It's interesting that a human synapse represents a connection between two neurons. So there's this concept of the synaptic gap. And in our model of the memristor, you can think of these two neurons as passive components, specifically as the two electrical terminals that the memristor has.
Ah, I see, okay. So now I can finally take a look at the chip. I'm curious, what do we have here?
Before we get to this chip, here's how it starts. We have a wafer onto which we apply one of the two electrodes, the so-called back electrode.
So this is a silicon wafer like this, and the back electrode has already been applied.
We've applied the backside electrode here, then the memristor material is applied over a large area here.
So I understand, it's a secret, okay.
And then, we can't see this here, it goes on top of this memristor material, then the top electrode materials on top of that, again metals, and then the whole thing is cut into 5 by 5 square millimeter chips.
Can I pick that up with the tweezers? Here, so that's the chip. It's a memristor chip. That's crazy.
And on the memristor chip, you can count how many memristors it has. There are 100 contact points, so there are 100 memristors on here.
Wow, you can really see these individual dots, and those are the individual memristors. A memristor consists of two electrodes separated by a metal oxide material, that is, a material containing metal atoms and oxygen atoms. What's special is that the memristor can remember, as the name suggests. That means that when you send current through it in a certain direction, its resistance changes, and it retains this new resistance value even when the current is turned off. So it remembers, or rather information is stored. This is only possible because of the material, and it took a bit of luck for Heidemarie Krüger's team to discover this composition.
In 2011, a doctoral student accidentally...
So from your research group?
Yeah, from my research group, a PhD student on my team was accidentally experimenting with other materials, and it just so happened that this memristor material ended up in the thin film by chance. And suddenly we had a solution for keeping the oxygen vacancies, which normally shift back and forth when a voltage is applied, in place when the voltage is removed.
It took a long time to find such a material, but the work was worth it because the material is a very crucial part of this. It has to be a material into which two types of mobile dopant atoms can be introduced. Dopant atoms are foreign atoms that are specifically introduced into the crystal structure of a material to alter its electrical conductivity. They must be able to move back and forth within the crystal lattice of the memristor. The mobile dopant atoms here are oxygen vacancies, as Heidemarie Krüger just mentioned. That is, sites in the crystal lattice of the memristors where an oxygen atom would normally be. These must be vacant, and with that this vacancy is, so to speak, positively charged. When a voltage is applied to the memristor, an electric field is created. This field pushes the oxygen vacancies in the material in a specific direction. Depending on how strong and how long the voltage is applied, these vacancies move and change their distribution within the material. This altered distribution of the vacancies influences the total resistance of the memristor. To demonstrate this, we connected a neuromorphic chip to a measuring device and generated a so-called current voltage curve. A voltage is applied and the current that flows in response is measured.
We are now applying a voltage to set a new state in this memristor. And then we'll apply a voltage again to see what state the memristor is in.
The measured curve shows how the memristor state is altered by the applied voltage. When the voltage is turned off again, the oxygen vacancies remain in their new positions. They are, so to speak, frozen or trapped by the built-in dopant atoms, which allows the memristor to permanently retain the set resistance value.
When the current reaches its maximum, we reduce the nominal voltage from plus 5 volts to 0, and the current that flows then is not the same as during configuration. From this point on, the oxygen vacancies remain in the position where you moved them.
The major advantage of this technology lies in the precise shape of the curve. It shows that the memristor does not change its state randomly. The resistance can be adjusted continuously and precisely, a crucial factor in making memristors usable for AI and analog computations. And that brings us to the areas of application. Okay, I have to admit, I think some of what's happening here is pretty complex. That's why I asked, can we do an experiment? And that's what we set up. So here we have, so to speak, the neuromorphic chip, and here we have 3 sensors. One measures temperature, one measures humidity, and one measures pressure. And now the big question is, what is the actual difference when you work with a neuromorphic chip? So what does it do with that, and why is it a good thing?
We've already discussed that the core components of this neuromorphic chip are the memristors. Each memristor has 2 ports, and we now apply data in the form of voltage signals to one port of a selected memristor from one sensor, and to the other port of the memristor data from a second sensor. Previously, we determined which physical correlations exist between the sensor data, meaning between the 2 selected sensors.
That means we combine, so to speak, temperature on one memristor and humidity on the other, and then on the other memristor we combine humidity and pressure, and then it's about the correlation. That is the relationship between these data points.
these data pairs, right? And we determined that beforehand, and the memristor now calculates exactly this relationship in real time. These are very complicated nonlinear functions with two variables, and we've configured the memristor so that it can do that.
The goal of these calculations is to determine the state of a system in real time. This is also known as data clustering, in which similar data points are grouped together to obtain information about a state. With this experiment, for example, you can now monitor the weather. This is particularly interesting for photovoltaic systems. Instead of capturing cloud cover with a video camera, the correlated sensor data can be used to determine what the weather is currently like. Something that in theory can also be done with today's system, but with two major drawbacks.
The big advantage, as we've already shown, is that if you cluster the correlated data, that is the result of the correlations, you achieve a much higher detection rate because you're much closer to the system and thus also to its current state.
While a classic AI achieves a detection rate of 89%, hardware-based correlation using neuromorphic chips achieves 97%. The difference stems from the fact that conventional AI systems have difficulty recognizing the correlations between data from multiple sensors when they are fed to the system simultaneously. Instead of first energy-intense loading the sensor data into software and then processing it there using AI, the neuromorphic chip processes the information directly within its hardware. This not only saves enormous amounts of energy, but also makes real-time processing possible. Since the computation takes place directly within the chip, the process is also completely transparent and traceable. Another important security aspect is that the chip immediately detects if one of the sensors is providing faulty data. But of course, processing exclusively on the hardware also comes with limitations, and that brings us to the challenges or the big hurdle of this video.
We see the first major challenge in simply increasing the number of memristors we incorporate into such a neuromorphic chip. So that's the most important thing, that we're able to manufacture memristors in large quantities using current technology, so that we can then build much more complex, much larger neuromorphic chips.
Because so far only 3 memristors have been used for this weather experiment, more complex tasks would naturally require significantly more. Another problem, the applications are still very specific and cannot be easily transferred. In addition, the interface currently still requires traditional electronics, so it's currently a combination of a neuromorphic chip and traditional electronics. This is likely to remain the case for the time being, but optimizing this interface is a major challenge. In long term, the goal is to be able to implement increasingly complex AI algorithms into the chips. The memristors will then be integrated with other conventional transistors to form AI chips. The first applications are expected to be on smartwatches or cell phones, for example. This would make it possible to analyze data such as vital signs or audio in real time with the AI, then helping to make decisions. So like an AI such as Claude or Gemini, but without an internet connection, directly on the device. But even more exciting are applications like autonomous driving or robotics, because that's where this significantly faster processing really comes into play. Latency can be truly dangerous, especially in these applications. And that's exactly why I find neuromorphic computer chips so exciting. They offer further opportunities to achieve a significant performance boost and solve some current problems. And saving these large amounts of energy naturally makes the whole thing very relevant for the future. I will definitely keep you up to date on this. Many thanks to TECHiFAB for the invitation, and thank you for watching and subscribing to the channel. And here you find one of my latest videos where I visited one of the biggest solar parks in the world. Please check it out, and if you like it, share it. Not so many people have seen it yet, and I'm really proud of this video, which was a lot of work. And yeah, if you like it, please check it out. And with that I say auf Wiedersehen, which means goodbye in German. Thank you for watching, your Jacob.